Hello everyone, this is Miss Spivey. Today we are going to cover ionic naming. And you're going to need your Unit 5 book. Open up to page 8 and 9. There are notes there that you can go back through and read if this video is not helpful. And you'll also need your periodic table. I am making this video from home, so if you hear my dogs barking, I'm sorry. Hopefully they'll be quiet. So we're going to start off with ionic naming, and as always, if I am going too fast or you need to pause the video, please pause so that you can catch yourself up and look at notes. So, all right, so here are notes for naming ionic compounds. Anytime you have an ionic compound, you should know, that's one thing I should have mentioned back on the first slide. If I'm assuming that by watching this video, you have mastered ionic crisscrossing, the crisscrossing method to write chemical formulas, because today we are going from the chemical formula to the name. So you're going to need an actual like working knowledge of where the subscripts come from and how to predict oxidation numbers and things. All right, so you also need to make sure that you know that an ionic compound is between a metal and a non-metal. Metal and a non-metal. Also, you can think about it as a cation and an anion. And mentioned in our last video is that the cation always comes first. That's just the general overarching pattern that you can find. So here are your steps of what to do. So the first step, you're going to name the cation. Do not change the ending on your cation. And if you have a transition metal, then you have to be able to go back through and find your Roman numerals. And I'll show you how to do that. The second thing you do is your compound overall binary, or does it have a polyatomic ion in it? If it's binary, it's super simple. It just ends in IDE, kind of like we did with covalent, except notice I have not mentioned any prefixes here. No monos, dis, tris, no meth, eths, propes, nothing. You just write the names down as you see them on the periodic table, and if it's a binary compound, it ends in IDE. Now, if you have a polyatomic ion within your compound, all you have to do is just write the name of your polyatomic ion, but the endings might change. Okay, so right now, the endings that you know for your polyatomics, some of them end in IDE, like hydroxide, cyanide. Some of them end in ATE, like acetate, sulfate, phosphate. But I'm going to teach you at the end of the lecture that some of those are going to start ending in ITE. So we'll cover that in a little while. All right, so let's look at some examples. NaBr. So I know that it's ionic, cation, anion. This is binary. Okay, I have two atoms only. So NaBr. Na stands for sodium. Br stands for bromine, so it's going to end in IDE, so sodium bromide. Again, keep those notes out next to you. If you did not copy this slide down, please pause the video, copy it down so that you can keep it next to you as I'm working examples so that you know where my thought process is going and why I'm doing the things that I'm doing. Okay, so sodium bromide NaBr. Next up, another ionic compound. This is also binary. It has two atoms in it. Mg stands for magnesium. If you're not a good speller, look at your periodic table. O stands for oxygen, so it's going to end in oxide. Okay, K3N. K stands for potassium. N stands for nitrogen, so that's going to be nitride. And so you might think, why didn't I put a tri in front of that potassium? Well, number one, this isn't a covalent compound. We don't use those prefixes. But let me remind you of what we did in the last lecture. In the last lecture, I gave you this name, and we said K is a 1, nitride is an N3, so that would be K3N. Okay, so remember the process, and that's going to help you understand why we don't have to use prefixes, because we have oxidation numbers and those are the root of our formula. Okay, all right, so Al2S3, Al stands for aluminum, S stands for sulfur, so that's going to be sulfide. Okay, so notice all of these examples have been binary with no transition metals. So these are very simple when it comes to naming ionic compounds. Okay, very, very simple. Let's look at some with our transition metals. So remember, in the last lecture, we talked about how these are transition metals. Tin and lead are in there, and they give us Roman numerals for the oxidation numbers. Okay, so anytime you're trying to find the Roman numeral, I always start by looking at what it's bonded to. So I look at the anions. Okay, these oxidation numbers and the charges on your polyatomic ions, they never change. Okay, so they're not going to try to trick you. Okay, so you have to remember that Roman numerals are tricky, and also that we reduce our subscripts. So we have to start thinking about if our subscript's been reduced as we're working backward. Okay, so let's look. FeCl2. I know that the name for Fe is iron. Iron is a transition metal, so I'm going to put my parentheses. And this is still a binary compound. Okay, so Cl is going to be named chloride. Now, to find our Roman numeral, I want to think about our chlorine. Okay, chlorine has a 1 as an oxidation number. There is a 1 here next to my Fe. So this formula has not been reduced. So this 1 came from chlorine. So that means that this 2 had to come from iron. Iron 2 chloride. And you're like, oh, that's not that bad. I'm just undoing my crisscross. Very true. But as you are undoing your crisscross, please start with your anion first, because its charge never changes. So FeCl3, I have iron, I need Roman numerals, I have chloride again, I see the 1 here with the Fe, so that I see a 1 there, so that means that this 3 came from our iron, so this is iron 3 chloride. Now, you might be thinking, oh, this is simple, I just look next door and that's the Roman numeral. Not true, because in this instance right here, okay? So oxygen, so Mn stands for manganese. I need Roman numerals. Oxygen is oxide, okay? Oxygen, let me pull up the periodic table to prove it to you. Oxygen always has an oxidation number of -2, okay? So when I look at this compound that I'm trying to name, I don't see a 2 anywhere in this formula. I see a 1 and a 1. And so this tells me, this is a clue to me, that my formula has been reduced. So if you think about it, what did the charge for manganese have to be in order to reduce to subscripts that are 1 and 1? The answer is a 2. So this is manganese 2 oxide. Okay, again, I looked at my charge for oxygen, saw that it's always a 2. I don't see a 2 in my formula, and so therefore I know that it's been reduced. So a +2 cancels a -2, and that gives us manganese 2 oxide. Okay, Ti3N2. So Ti is titanium. It's a Roman numeral, and so transition metal. N is nitride. Okay, when we undo our crisscross, nitrogen has a 3 as an oxidation number. There's my 3. So that means that this 2 had to come from titanium. So this is titanium 2 nitride. Okay. PbO. Pb is lead. Even though lead is in a weird spot, it is still considered a transition metal. It's within my boxes over here. So PB is lead. It needs Roman numerals. O is oxide. Oxygen always has a charge of -2. I have 1s here, so this has been reduced. This is lead 2 oxide. And you're like, oh, well, these formulas are very, very similar. That's true, but one has a 2, one has nothing but 1. So the oxidation number for lead had to have changed. So I have lead something oxide. So the charge for oxygen is always a 2. I don't have a 2 here next to lead as I'm following my crisscross method. So that means that my formula has been reduced. It's reduced to 1/2. So that means that if I had a 4 here, so PbO4 would reduce to PbO2. See, the 2 and the 4 reduced to 1/2. Again, if you haven't watched the video for how to crisscross, this probably seems crazy to you. So make sure that you have mastered the crisscross method and are completely sure of where the values are coming from. So this is lead. I need to make my room IV oxide. Okay, so again, oxygen always has a +2 charge. I don't see a 2 there. So lead had to be a +4 to get it to reduce. Okay, so all we have looked at so far have been binary ionic compounds. Now I want to start looking at compounds that have polyatomic ions in them. So you have to know your polyatomic ions. You just have to know them. So as you're looking at these words on my slide, you should know their formulas and their charges. Okay? So the charges of your polyatomic ion never change. What we're going to start talking about are the actual chemical formulas that will change. Okay? So not all of your polyatomic ions are going to try to trick you. This list over here of won't change, hydroxide, ammonium, acetate, anytime you see that formula, that's the name. Okay, you're just recognizing it because you've been taking quizzes on them since the first day of school. Now, this tricky group here can change. And so what we are changing specifically are the number of oxygens in our chemical formulas. Okay, so let's look at that a little bit deeper. So here with all right, so we're looking deeper at our polyatomic ions. So you have memorized all of the polyatomic ions here on the left-hand side of the screen. This is exactly what you've been taking a quiz on all semester. So what I want you to see are that these polyatomic ions all end in ATE. Okay, so this is their normal amount of oxygen. So nitrate normally has 3 oxygens, carbonate usually has 3, phosphate has 4, chlorate has 3, sulfate has 4. Okay, so when you see a chemical formula like this, you think, oh, that looks like nitrate, but my oxygens have changed. So we've only lost 1 oxygen. So instead of being nitrate, this is going to be nitrite. Okay, CO2 -2. Instead of being carbonate, this is carbonite. Okay, PO4, PO3 would be phosphite. ClO2 is going to be chlorite. Okay, SO3 is going to be sulfite. All right, so you memorize the polyatomic ions in their normal amount of oxygen, so therefore they have an ATE ending, but now their number of oxygens can change. Okay, so we lost one oxygen. Okay, so down here, if we add 1 oxygen, I'm going to use this prefix per and still the ATE ending. So here if you look at chlorate, ClO3, down here at ClO4, I have added one oxygen. So this is going to be perchlorate. Okay. Now, you can also lose two oxygens. So instead of being chlorite, ClO is going to be hypochlorite. So the hypo and per have been the only prefixes that I've mentioned with ionic compounds. Okay, so these polyatomic ions will not always change, but they can. And so I just want you to be aware of it. So if you need to copy these examples down on your notes, that's fine. But just please make sure to recognize when we have normal oxygens, it's an ATE ending. When we start changing the oxygens, you could have an ITE ending, as well as adding in a prefix. So let's look at some examples. Okay, so NH4C2H3O2. You're like, holy cow, that's a whole mess of atoms. I don't know what to do. Well, hopefully all of these quizzes have paid off and you recognize that this is a polyatomic ion as well as this. So this is going to be ammonium acetate. And if you don't know why, the answer is you should have it memorized. Okay? Al2SO43. Al stands for aluminum. This isn't binary anymore. I have a polyatomic ion. So SO4 is just as you've memorized it. So that's aluminum sulfate. Al2SO3. So here is aluminum. But I don't have sulfate anymore. This is sulfite. Aluminum sulfite. Okay. KMnO4. Here's potassium permanganate. Okay. MgOH2. So here's magnesium hydroxide. Gonna run out of room. So all of these, I have not had to think about Roman numerals. I haven't had to think about crisscrossing or anything. So now let's look at some with transition metals. So Cu stands for copper. I need Roman numerals. And I hope that you recognize that CO3 stands for carbonate. So now we have to think about what the charge is for carbonate. So that should be a 2. I don't see a 2 here next to my copper. And I also don't have a subscript out behind my carbonate. I only have one carbonate group. So this means that copper had to be a +2. So copper 2 carbonate. Okay. So Fe stands for iron. It needs Roman numerals. ClO3 you've had memorized since August, I hope. So I have iron something chlorate. Okay, chlorate always has a 1 as a charge. So here's my 1. My formula has not been reduced. So this is iron 2 chlorate. But then if you look at this formula, I have a little change here as well as here. So we have to take that into account. So iron something. And instead of having chlorate, now I have chlorite. Okay. And again, when we think about our Roman numerals, chlorite's going to have a 1 charge. So that means that this 3 had to come from iron. So iron 3 chlorite. Okay. Not that bad. Just takes a little practice. Takes some slowing down. Let's mix some up. Let's try a little bit of everything. Okay. So Pb is lead. It needs Roman numerals. PO4 is phosphate. You've had that memorized. So the charge for phosphate's always a 3. There's the 3 there. So that means that this 2 had to come from lead. So lead 2 phosphate. Okay. CuI. This one's binary. Yay, binary. So that means it has to end in IDE. Cu is copper. It needs Roman numerals. I is iodide. So when it comes to writing our Roman numerals, iodide always has a 1 as an oxidation number. So both of these are 1s. Copper 1 iodide. SNO2. SN stands for 10. I need Roman numerals. This is also binary, so it's going to end in IDE. So when we look for Roman numerals, start with oxygen. Oxygen always has a 2 as an oxidation number. There is no 2 there, so this has been reduced. So 10 had to be a 4. So again, just to prove it, SN2O4 reduces to SNO2. Okay, so remember, reducing your formulas can make this tricky. All right, this one down here at the bottom, Ca3P2. Ca stands for calcium. This is binary, so P is going to be phosphide. Again, if I'm going too fast, pause the video, try the examples on your own, and then see if you're right. It's a great way to practice. So Na2CrO4, Na is sodium. CrO4 is chromate. So here is sodium chromate. NH4, NO2. These are both polyatomic ions. Okay. NH4 is ammonium. And NO2 looks like nitrate. Remember, NO3 minus 1. So this has to be nitrite. Okay. So here to wrap up the video, if you are feeling really discouraged and you're like, I really hate chemistry, why are there all these rules? I don't understand. This will take lots of practice, okay? Even if you do a worksheet one time and you have the answers, go back and do it again. Go back and do it again. Because tomorrow or the next time you come to class, we are going to start throwing all of our different naming systems together. So you have to know how to name ionics, covalents, organics, and you still have to learn acidic nomenclature, okay? So really sit down, slow down, and be patient, and really try to master this. So just ionic naming is located on page 10 and page 11. And then other videos will tell you where to go to get practice with mixed naming. So please go back through, replay parts of this lecture if you need it, copy things down, go slowly through the examples. And as always, if you need help, please see one of your Chem Squad teachers. Thank you.